Thank you, Sarah, for the really nice talk. So now we will be starting the Q&A session. Please raise your hand if you have a question for Sarah that you'd like to ask on Zoom. If not, I'll start to read the lively thread on Slack. All right. So while folks are putting their hands up, I can start by asking a question from Murat Demirbağ from AWS. So the question is, where does the name come from?
Yeah, so one of the things that Kangaroo does is it decides between memory and klog, and between klog and kset whether it wants to keep the object. So it's like constantly like rethinking or like ruminating about objects, and kangaroos will ruminate on their food. So that's where it comes from.
Okay, thank you. The second question comes from Vishwanath, who's a graduate student at Emory University. So the question is, how does this approach compare with the SegCache, which uses a slab-based memory allocation model?
Yes, so SegCache is primarily designed for memory allocation in like actual DRAM, which means there's different constraints on terms of placement and lifetime of the devices versus if you're trying to cache on flash. So we're really concerned in Kangaroo about like the minimal write endurance on flash, in addition to DRAM overhead constraints, which SegCache also has to deal with. But because that we're actually caching on flash, we have different constraints for what we can actually do in the cache.
All right. The next question is from Jongyu Park, which is actually here. So can please unmute yourself and ask the question.
Hello, can you hear me?
Yeah.
I'm Jongyu Park from Sungyeong University. I'm curious if any temporal locality across objects has been observed in the experiment. For example, are the objects read as they are written usually, or also I'm curious about the skewness or characteristics of the workloads. And the second question is, how big is the merged object that goes from DRAM cache to klog and klog to kset on average?
Yeah, so for all of the details about the traces that we used in our paper, I would refer you to prior work, the cache load paper at OSDI that my group published. And then for the Twitter traces we use, there's a paper from Jen Cheng about those traces. But about your specific questions, for temporal locality, we do see amount of temporal locality. We have, for instance, at Facebook, we have a 7-day trace. You can definitely see the set of objects change as over time throughout the trace. And that's really important to take into account on your flash cache, because otherwise you would just put all of your objects in at the beginning and never change the objects in your cache. And the workload's pretty skewed. And then in terms of merged objects, so we keep track of each object individually, and objects are around an average of 200 bytes to 250 bytes, depending on exactly what workload we used between the Facebook and the Twitter, and then the production deployment that we had at Facebook.
Thank you.
All right, we have one more question from Brian Kim from Syracuse University. I don't see him in the panel, so I will read the question. Brian is saying, very interesting work. Can you talk a little about the data placement policies across the SSDs used in your system, or is load balancing a non-issue in this workload?
So yeah, Kangaroo focuses on what happens once you send the request to a single server with the flash device on it. So within that context, it's not really a problem to load balance across the system. Everything just goes through one interface to the flash device. If you have multiple flash devices, you could potentially put them in RAID on the system or something like that. Or just expose them as one large flash device to the system. For load balancing outside of the system, I encourage you to refer to other load balancing papers because we don't tackle that directly.
All right, thank you. We have time for one more question. Edward, can you please unmute yourself?
Yeah, and there, my video is on. So also I'm from Augusta University, and my question is, it seems like you have this balance between the K-log and the K-set to help manage this trade-off, and when a object needs to be evicted from K-log, it goes to K-set, and you find these objects to coalesce with it. Well, is there also a tuning knob or a way to affect this trade-off with the eviction policy from K-log? Because I would imagine changing the eviction policy changes how likely you are to find objects that you compare to evict to K-set.
Yeah, so we do that to some extent. K-log itself uses FIFO eviction policy, so first in, first out, on the segment level, so large granularities of the log. And once objects are evicted, they go through the threshold emission policy, which means that if there's not multiple objects that are going to map to the same set in K-set, they'll be evicted. However, that eviction actually, if the object's popular enough, so if we're really worried about losing misses or losing hits because we're going to evict that object, we'll readmit it into K-log to give it a second chance of getting more objects that'll map to the same set in K-set, essentially. So we do play around with some of the eviction there.
Okay, but it sounds like it's just strict FIFO when it gets to the end of that circular buffer, it needs to get evicted.
Yeah, because that's a very small portion of Flash, we spend a lot more time on our eviction policy in K-set, which is where objects spend the majority of their time on Flash.
Oh, okay.
So we implement a Wrapup eviction policy, which all the details are in the paper. I encourage you to look there for that.
Okay, thanks.
Yeah.
Okay, we have one more minute, so I'm going to ask a question as well. So you explained very nicely how the Kangaroo design works to evict to block-based devices. Can you comment a bit how this design would generalize, say, if you wanted to use persistent memory instead of flash cache? If that makes sense at all.
Yeah, so for persistent memory, it's gonna depend on exactly what the constraints are in your persistent memory. If you have like an Optane SSD, for instance, you're still gonna end up with that 4K write granularity. So, but your write endurance, depending on what numbers you're actually looking at, may or may not be a lot better than Flash. So if you're still running into that write endurance limit, Kangaroo is still gonna help you with that P memory constraint.
All right, thank you very much. Let's thank our speaker one more time, and congratulations again for the best paper award.
Thank you.
Now it's time for our second paper in this session.
Caching billions of tiny.
Okay. So, Sarah here?
Yeah, I'm here.
Good. It seems that there's no question posted on the Slack. And if you want to ask questions, you can either post a message on the Slack or raise your hand in Zoom, okay? So it seems like you combine the K-set cache and log together. And how can you reduce the miss ratio? Because you just combine them together. So what is behind you can reduce the miss ratio?
Yeah, so there's two main parts to reducing the miss ratio. First, Kangaroo is able to use more of the flash capacity because it gets around both the DRAM constraint that you see in just a log structured cache approach and the write constraints that you run into with a set associative cache. So for the log structure cache, you just can't index most of Flash, so you end up not being able to use a very large amount of Flash. And on a set associative cache, you have to write a lot, and one way to decrease the writes is to basically over provision your device by a large amount, say like something like only use 50% of the Flash capacity, because that'll reduce the amount of cleaning that you have to do in the device. So by reducing both the DRAM overheads and the write overheads in Kangaroo, we can use more of the Flash capacity to actually cache, thereby our cache is bigger and our misses are reduced. The second thing is Kangaroo introduces an eviction policy called Wrapup, which is a variant on a RIP, which is a processor cache eviction policy that uses recency information to decide what to evict from each set and K set. And the big distinguishing factor about Wrapup is we can implement it with only a 1 bit of overhead in DRAM for each object in K set.
Okay, so two things, right? So for this, the first one is to increase the usage of the flash storage, and the second one is you just integrate some method that was not used by previous works to precision, right?
Yeah, traditionally eviction policies have been challenging on Flash because they either incur a lot of extra writes or you need a lot of like metadata tracking to implement them. So we were able to implement a smarter eviction policy basically with little overhead.
Okay, let me see. Still no question in this on the slide. So my other question is, it is kind of interesting to use SSD as the cache. And then you can see that both the front end and back end, you will store the objects in the maybe storage system, something like a database system. And also you use the front end and the cache also use the persistent storage like flash storage. So my question is, can you just combine them together to form maybe a unified storage for both cache the data and for cache?
Yeah, so you could potentially do that. One of the nice things about separating it is that your cache doesn't need all of the consistency mechanisms that a database needs.
Okay.
So for instance, you're like in our paper, we rely partially to reduce rates on being able to evict objects whenever we want. You can't just evict objects from a database system because then you're losing data. So it's nice to split them, and it's nice to split them on servers too, so you can basically have more CPU usage. You're not running into as much of a CPU bottleneck for both systems.
Okay.
And then part of the reason we use Flash in the paper is because it's used in practice, because DRAM only caches tend to be very expensive as you need to scale them up. So in practice, many different companies, including Facebook, use Flash as a caching medium.
Okay. So maybe, what is the, for example, what is we just drop out the cache on the flash storage and use maybe, use cache in DRAM, and maybe we can just improve the performance by throw away the cache on flash. So what do you think? What is maybe the better choice for using more DRAM for cache, or using little DRAM for cache, but just seek for the data storage?
Yeah, so in the system we're looking at, which there is actually DRAM caches. So there are DRAM caches in front of us because we're looking at applications, for instance, that go all the way to a user's like Facebook or Twitter profile, right? So there's many layers of caching. So the thing is, once we get all of those requests back, by the time we get to the flash cache, we have patterns that are pretty, that have lost a lot of the very easy to cache things. So we really need those large caches of flash caches to basically be effective at all as like a cache, and keep the load off the database servers so that the database servers aren't like overrun and you don't need as many database servers to handle the load.
Okay. So consider about the consistency issue because you use the cache for the backend storage, right? So what if we take a consistency into the consideration? So what might be the influence maybe on performance or other kind of issues?
Yeah, so at a first level, we assume that you have some other form of consistency that's happening outside of the cache. So we assume that Kangaroo is not actually going to be the persistent for any of the objects. So we have a write through cache essentially.
Write through cache. Okay.
Yeah. And so that means like sometimes Kangaroo will get like invalidations or whatnot in production. So we have to deal with some amount of invalidations, but in general, we can handle those pretty well.
Okay.
And then you could potentially see implementing something that had consistency built into it where you had to track objects. I think you could implement that on top of Kangaroo. We just don't, because the system we're implementing it into already has a separate consistency mechanism in place.
Okay. There's still no questions on Slack and no raise up on Zoom. So, okay. So how we want to, so how can I bring him up? Okay.
Hi.
Howie.
Hi, Howie from NUS here. It's a bit of a generic question, but just wondering any future research directions that you might have, or how are you going to develop this further?
Yeah, so one of the things that we've been interested in is different emerging Flash interfaces. So for instance, zone namespaces, which is an SSD and hard drive interface, because one of the things we did in Kangaroo was really reduce the write amplification we're getting at the application level, but we still are doing random writes to an FTL layer, which means that you get a lot of write amplification at the device level. So one of the things we've been interested in is seeing like what you can do with something that's not necessarily like the best case for SSDs. Random writes in general aren't. What you can do in terms of optimizing that if you have more control over what's actually going on a flash device.
And thank you. And another question is this being deployed at Facebook now, or Twitter?
Yeah, we've been working with Facebook to get pieces of it into deployment.
I see. Cool. Thank you.
Yeah, and we deployed it in shadows in the paper. We have results from that.
Yeah, I already see that. Okay. Thank you, Sarah. So we can just to the next paper. Okay. So next paper is Yoda, a host device co-design for strong predictability